All right, yesterday we did a activity at the end of class that was really fast. It was lightning fast. It was Speedy McQueen fast, okay? And what you did was you explored the conformation of energy levels. The Bohr model, the 1800s model of the atom, offered us a really valuable concept that in the atom, electrons exist in distinct rows, distinct energy levels, exact rings. They're not just a free for all chaotic cloud where electrons just float. No, they actually have specific placements. And we see that on the periodic table. According to the Bohr model, we have 7 possible rows. Now we fill the rows from the lowest to the highest. So row 1, energy level 1, shell 1. Row 2, energy level 2, shell 2. However you want to say it, okay? And we know that each row has a unique amount of seats that it can hold. It maxes out at some point, and that's when you're asked to move up to the next one. It tells us how electrons are distributed. Because in the nucleus, we just squish the protons and the neutrons together, like squishy squish, okay? But when we talk about the atomic structure, the electrons really matter because we also know that a specific set of the electrons, the valence electrons in the highest energy level, in the outermost ring, okay, in the highest row, are also the ones that bond. They're the ones that do all the bonding and interactions with the other atoms. So we know valence electron and the idea of electron placement is super important to understanding the atom. And that's what we were studying. And yesterday, hold, pocket. Okay, that's what we were studying through the flame test was how do we see this in lab? Because there's a bunch of theories. I could create a ton of models and say, oh, look, it exists. Where's the actual evidence? Well, the lab was the confirmation that, yeah, we do know that this idea of energy levels being a thing is real because elements will portray certain colors, certain wavelengths of light, certain energies of light when their electrons get excited and jump distinct amounts of energy. They jump up and down. And that series of jumping and then falling back down to what we call the ground state, the natural state where everything exists, the lowest energy level state, releases an exact amount of energy based off of that exact jump. And we see a unique light pattern. Okay, so that was what yesterday was about. And I'm just going over this really quickly to remind you, one, you need to submit this. This is something that goes in your grade as we look toward progress reports. Okay, a completion of this, and some of you already have. But out of curiosity, what was the unknown that you guys identified based off of the light color, based off of the unique jumping pattern, based off of the unique energy level change, based off of the unique energy release? Okay, see how I'm repeating all of this to show you the connections. Okay, what was the element that was part of that compound, specifically the metal, based on the color, Aislinn? Potassium. Now, if you did not get potassium, please do not write that you got potassium because that makes you a liar. And we don't lie, okay? What we do say is, okay, I know it was supposed to be potassium, but this is what my data showed me. So notice handy dandy, one of the first questions I ask you is state possible sources of error, right? So what were some sources of error for you guys, whether you got potassium or not? What were some issues that you probably saw in terms of accuracy and precision in the lab? Min.
Sometimes we hold this region, hold this like right.
Yeah, the placement of the wood stick in the flame. Okay, that's definitely a big one. Okay, what's another one that was created an inconsistency? Hallie. You have to what? Yeah, you're estimating. That's definitely supposed to be an E. You're estimating color with the naked eye. And while the naked eye is quite impressive, because you can see a lot, you also can't see that much, especially when you're talking about minimum wavelength difference. Minimum in terms of the whole spectrum of color, your golden brown versus your brown ain't gonna look that different to your eyes. Because that's where, by the way, pigment comes into place. Pigment is a little easier to spot. Wavelength based off of wave energy, based off of wave distance between the peaks, that's a little harder to tell just with the naked eye. Okay. Now, if I gave you a thick oil painting, maybe you could tell me the difference, but you were going off of a flame. And by the way, that flame had its own color too, just from the natural methane gas. So some of you guys already noticed that some of the stations you had a really hard time telling, is that a pink orange or is that just the orange from the flame originally? It's really hard. Okay, that was just some of them. They don't have to all be the same. There's a lot more errors like flame intensity, like flame different original flame color. Like you could list several things, right? Ground state, okay? What is the ground state for an electron? What do we say? What do we say, Mary?
Like usual low energy state.
Yes, it's the lowest energy state, or what we could call arrangement. Where is the lowest energy place? I know I'm misspelling this horrendously. Where is the lowest energy place that we could put it? Okay. One could say it is the natural and desired state, right? So then what causes an electron to be excited? What must happen to it? It must what, Alex? To be excited, should be excited, but what must happen for me to get there? I have to absorb what? Energy, exactly. So you have to absorb energy somehow. So whether I shoot you with a laser beam of light, or whether I put a freaking fire on your butt, okay, you're gonna get energy, right? You're gonna get energy. It's gonna transfer into you and be like, oh, okay. And so what happens to them? What we see is you could draw a ring. I don't really care. You could draw a ring Bohr model style, and you could have done this. You could have said, well, that was an oval, whatever. Okay, interesting. Okay, you could have drawn something like, oh, I have one electron and it jumps up. And there we go. And now it's up here. Now its new placement is up here, an energy level. You could have done that. You could have drawn it like this too. You could have said, well, energy level wise, I don't want to draw a full ring. I just want to show in general that there's distinct exact energy levels. Juan, look at me, not the machine. Okay. The distinct exact energy levels. I start here. That could be the same as this. Like I could just be showing you a snapshot of it instead of the whole ring. And it goes, okay. And then we have, it's right there. Those are acceptable. The big idea is that you're showing it jump. Okay, it jumps. It jumps to another energy level. You could have drawn 7 rings and said that one jumped all the way to 7. I really don't give a flipping doodah. Okay, but the idea is that it has to jump. Okay, and so what happens though is, does it stay that way? Does anything stay floating in the air after high energy? Do you stay high energy? No. So what does it do? It falls, baby. Okay, so it falls. So I'm gonna copy paste. That was definitely supposed to be a copy paste. Oh man, jeez. Copy, paste. And what we say is, what happens? It falls back down. So this, yeah. Do you think it'll pick it up? Yeah, look at that technology, man. So what happens is that purple one that was excited now falls back down. And what happens? What does it release as a result? It releases light energy. Exactly. So this is a release of energy. And by the way, you could have inputted energy. You could have said an input here if you wanted to get consistent between the photos. Okay. You could have done something, adjusted this photo to be, instead of jump, we say it has now, this purple, where it was, has now what? Fall. Oh, gee willikers. Fallen, right? And now it returns to ground state. Okay, so now we say it falls. Timber, right? The Kesha song. Were you guys old enough to know that song? I'm going down. I'm yelling timber. Yeah. So, anyway, it falls. You could have said it falls from 7 to 3, then from 3 to 1. Sometimes it falls in series. Sometimes it doesn't fall in one giant go. Either way, you definitely want to get back to the ground state. You definitely want to get back to where it originally was. Okay. So then out of curiosity, could somebody offer their explanation for why we see colors in fireworks and sparklers? Like when I was at Disneyland, why do we see colors in sparklers and fireworks? I'm looking for someone who doesn't normally offer an answer. Danny!
Like they use like certain chemicals in the explosion to make it look colorful.
Okay, so what if specifically, so those chemicals have unique what?
Wavelengths?
Yeah, they're good at, they have electrons in them that are going to create a unique wavelength when, where's the energy come from? We know that in order to create light, you have to excite something and then let it fall back down. So what's happening? We explode the fireworks, what's happening?
Jumping.
Yes, the atoms in that chemical mixture has electrons inside of them are jumping, okay? And they're from the explosion. The explosion is the main source of energy. Boom, okay? Then what happens is when they explode, where's your source of energy now? It's tapped out, man. You used it. So what happens after you jump?
The wavelengths create based on
Yes. So before you even have that though, you have to do something. After getting excited to jumping, you have to after I jump, I have whatever goes up must come. Yeah, so your electrons, after getting excited in the firework explosion, fall back down, and then that releases unique energy wavelengths, which release the unique light colors that we see in the sky and go, wow. Okay, so sounds like, oh, things, right? Sounds like, oh, duh. But reality is somebody figured this out. Like somebody figured it out before you, and they marketed it and made money. Which, by the way, is one of the ultimate goals of chemistry as well. None of your ideas are really worth much unless they actually make money. So sometimes, not to be completely, monetary, sometimes if you're like, I don't get the point of chemistry, it sounds so stupid, and you're like going through like a moment in your head where you're just having like a real high school or teenage moment toward chemistry, just remember all the rich people in the world got rich because chemists figured out how to market things. Chemists were the root of your clothing, how to create dyes, how to create your cell phones, okay? Chemists figured all of this out, chemists and physicists. So if you're ever like, this is dumb, just get selfish for a second and be like, but I could be rich. If I push this, might be the next rich person, okay? So, yeah. But anyway, kind of cool from a just inherent area of, hey, I actually understand why certain things work the way they do. Like, why do I see color? Okay. But in a very selfish way, hey, money is nice. Marketing is nice. Okay. Being known for something is nice. Not the ultimate goal, but it's nice. Okay. So don't forget to turn this in. And does everyone have their personal periodic tables out? Let's switch over to notes. Personal periodic tables. Okay, so hopefully everyone has done that how to color in your periodic table video. Remember, that was a homework check. So don't forget, for progress reports, you should be submitting homework checks. I put in the title of the homework check what evening homework you should be submitting, or for one of them was, I literally put color in periodic table proof. So you should be submitting proof on Canvas that you've done that, okay? But hopefully everyone has. My TAs are tracking it, okay? And you guys probably got SPD and F. You guys wrote somewhere on your periodic tables these zones called SPD and F. And you're like, what the frick? What is that? That doesn't make any sense, okay? I'm going to teach you what that means today. Because what today is about is we're going to graduate from the Bohr model, because the Bohr model is really insufficient. Why? It literally takes out more than half of the periodic table by removing transition metals. That's not a very useful model if you have to ignore half of the things it should be talking about. So the one thing that we're going to keep is what from the Bohr model? What was the one thing I keep on emphasizing that the Bohr model did give us? Yes. Energy levels. We're going to keep that. Obviously, it's still part of the periodic table. We see that. I keep on talking about it. But we need to move on to a more updated model that allows us to, one, more specifically name where an electron is, and two, acknowledge that other elements exist. In fact, much more elements exist than just those that are on the edges and fit the 8 electrons perfectly, okay? So we're graduating to what we call the quantum mechanical model, or the quantum model. This is the second most up-to-date model. We're gonna max out here in our class, but if you advance into chemistry, you're gonna learn about a model based off of calculus, derived calculus, known as the molecular orbital theory model, which is completely the calculation of wave zones where electron waves can exist. That's for looking forward for any of you that study chemistry at the collegiate level in like junior, senior year of college. Okay, but this is a pretty advanced level. Like even the AP accepts this. Like this is pretty accurate. It's a little bit more tangible than the other one, the highest one. So, what was your question, Danny?
Are we ever to use like the other model ever again?
Yes, for your test tomorrow. Because remember, what is valuable is the energy levels, and we keep that with every single model. Every single model has this idea of energy levels, energy, distinct energy places, distinct energy zones. Yes.
Everything for the test tomorrow, we've already done, right?
Yes, yes, yes. And when we break off at the end of class to do station rotations, you'll see some repeat and some new station questions that really emphasize the tests tomorrow, which is Coulombic attraction and periodic trends, as well as Bohr model. Okay. So, and I'll go over a little bit at the end too. Okay. So, but we're going to stay right now in the zone of moving in our progression of the atomic model. We're going to stay here for right now. And the quantum model tells us more exactly where the electrons are. Because right now the Bohr model just tells us it's in a ring. But I could put the one electron in a ring. I could put it, I could put it anywhere on the ring. Does it go here on this side of the ring? Does it go here on this side of the ring? Does it go single, single? Does it double, double? Right? We don't really know. We just know it goes in that ring. It's kind of like saying you can sit in any seat in the first row and you still probably be like, well, what seat? You're a little bit more specific. We're going to get better at naming exactly what seat that electron belongs in, where exactly that electron is in the atom, because that location of the electron matters. Okay, it matters. So what we know is that the quantum model, all right, is the modern, not the most modern, but the modern model for electron arrangement. Okay, and location within an atom. And there are 4, okay, levels, or I don't even know how to, levels or ways, or how do I put this? There are 4 levels or categories for writing or identifying what we call the address of an electron. Okay, so the quantum model has 4 series of organization, 4 layers, 4 levels. Maybe I should put layers. That might be a better word, layers. Okay, slash categories for writing the address. You can kind of think about it as like your physical address. You have your country, your state, your city, your street name, your house number, right? Like you can go real deep with locating where you are. And if you really want to get real good, coordinate plane, right? Where's your coordinates, right? Same idea here. We're using a multiple series of levels of narrowing down the location of the atom. It's in this zone, and this energy level, this orbital, this suborbital, this place. Well, that's what we're doing. We're zooming in on where the electron is within an atom. Okay. And so the first thing that you've already learned is you've actually already learned about the first level in the quantum model. So there's first level, the first layer, I should say, first layer. And I don't know why I deleted so many notes, but whatever, doesn't matter. I'll write it in. So the first layer is known as what we call the energy level layer, right? The general energy level, or the technical term in this model is called the principal quantum. Okay, the principal quantum number is what we call it in the quantum model. And this, by the way, you can kind of think of it as analogous to your state. What state I'm in. California. Where am I generally? Okay, row 1, row 2, row 3. You already know this. This has already been told to you. This is what we're keeping from the Bohr model, right? This is what we're taking from the Bohr model and we're keeping in the quantum model. But then the second layer, because by the way, that's where the Bohr model ends. It's like, it's in this, done. Okay, But now we need to get more specific and say, okay, well, what area, what zone of the energy level are we in? That's this level. This is the second level. The second level is known as the orbital. Okay, or you can kind of think of it as like a zone, or according to the address analogy, the city, the zone or the city of the electron. Okay, and the orbital model, by the way, differs from the Bohr model. It's different than the Bohr model because the Bohr model called it orbits. So notice, you might hear orbits and orbitals. Orbits was actually a reference to the energy levels up here, but you'll get confused and you'll accidentally call orbitals orbits, which is one, just the Bohr model, and two, only talking about energy levels. So be very careful that you don't mistake orbitals for orbits or shells or something like that, okay? That's particularly for the state testing. They might say Bohr model orbits. They are not the same as orbitals, okay? And by the way, if that confused you even more, just ignore the word and pretend it doesn't exist. That's also one way not to get confused, okay? So we call them orbitals or sublevels. They're also called sublevels. So what you see here is, let's take a little arrow. Let's unpack this together, this second level of organization, the city or the zone. So these are actually, what we're turning now is into a 3D understanding of the atomic model. So the Bohr model is very 2D. It's like, here's a ring, bring, okay? But the reality is the atom's 3D. So one benefit of the quantum model is it not only is more specific about where the electron is, but it also takes on now a 3D aspect of the electron. It pops it out. And it says, okay, these energy levels are not just rings, they're 3D states, they're 3D areas with exact energies, but they're 3D. Okay, kind of like whoosh, okay? If you put like a bubble around us, this would be a bubble with a distinct amount of energy, but now 3D. And then within that bubble, we have specific zones, 3D zones. And those 3D zones are generalized by the shape that they make. So zone 1 is known as the s orbital. You can call this like zone, S zone. You could say it the S zone, right? And what you notice about the s orbital is it is a spherical, okay, a spherical space where electrons can exist. And particularly, it's a space where only 2 electrons can exist. It maxes out at 2 electrons. Okay. The next zone, again, we're in some state. We're in some state with a general energy level. We're in some state with a very specific, okay, energy dynamic. But then we're in zones in that space, 3D. I live in this 3D area, the S area, the S zone. Well, that's not going to make up all of my energy levels or all of my states. So I need to consider the other parts within my state, the other cities or zones. And the second zone, I'll change colors, is known as the p orbital or the p zone. Okay. And this is what we call a dumbbell shape. And it's actually made of 3 suborbitals. It's made up of 3 based off of orientation. Based off of 3D orientation. So together, those dumbbells going on the X and Y, plus the dumbbells going on the X and Z, plus the dumbbells going on the Y and Z, together create the P zone. Kind of like a city. Like, just think about how much we zone and categorize cities. If you really want to go crazy, study how like East Asia like categorizes. I don't even understand like province versus city versus town. Like, it's crazy. Okay. So this dumbbell shape is made up of 3 suborbitals. Okay. And what we see is that together they hold a max of 6 electrons. So that means each suborbital holds how many? if I have a max of 6 between all 3 of those p's, 2. Each suborbital holds 2 electrons. So it's this plus this equals my p zone. Those 3 equal my p zone. Okay. So far, the S and P orbital match up exactly actually with the Bohr model, because notice we're maxing out at 2 plus 6, 8. Where does the Bohr model max out for where each energy level can hold? 8. Now here's where we differ from the Bohr model. Now we're getting into, other than the whole 3D part, okay? Now we're getting into, okay, how do we account for transition metals? This is where the quantum mechanical model far exceeds what the Bohr model can do, because now it can account for those really long 10 slot, 14 slot zones on the periodic table. This is where we see the transition models be acknowledged. Metals be acknowledged. Okay, and so what we say then is we have another zone that the Bohr model just did not know what to do. Wow, this is getting worse as I try to rewrite it. Acknowledged. Okay, the d orbital is a really weird shape. I don't even exactly know how to describe the d orbital, I gotta be honest. Okay, but you kind of think of it like a 4-leaf clover plus a squished donut. Okay, so it's this plus this plus this plus this together equal the d orbital. So what do you see? It has 5 subshapes or suborbitals. Okay, based on shape and 3D orientation. So we have a max of 10 electrons. Oh, that's kind of interesting. If we look at the periodic table in the D zone, where you guys were asked to label in the video, how many boxes are in the D zone in each row? Count your boxes. I'll let some people write and then I'll switch over to the periodic table. 4-leaf clover. So if we go to the D, one second. If we go to the D block, look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. S block, 1, 2. Max of 2 electrons. P block, 1, 2, 3, 4, 5, 6. Max of 6 electrons. D block, max of 10 electrons. Can anyone tell me what the F block is going to hold? Carlos? F block? Think about the max amount of electrons it can hold. F block is down here, these 2 rows. Right here. How many electrons can it hold based off of the box count across a row? 14. How many suborbitals do you think F block will have if it can hold 14? 7. You're seeing the pattern. Excellent. So, yeah. So, max of 10. 5 suborbitals. How many does each suborbital hold? 2. Okay, oops, I should say suborbital. Okay, F block. Okay, this is even weirder one. I don't even know how to describe this one. It's literally just like, I call it the don't F with it block. Because one, it's where all your nuclear stuff is. So this is where like your nuclear chemicals are. A majority of your nuclear chemicals exist in the F block. And I'm not even going to try to describe the shape. It's just weird. But what we do know is it has 7 suborbitals that make it up. Okay. Based on shape and 3D orientation. So this plus this plus this plus this plus this is equal to the F block. All of those together equal the F block. And it does, like, look how weird it gets. Like, what is this? We don't know. We don't know. But this is what we have generated through series of tests as this shapes relative in space that together make up the F block. And by the way, each of these holds 2 electrons somewhere in there. Somewhere in there, there's 2 electrons. So it's kind of weird, but if you don't think about it too much, it makes sense. Yes.
Is it possible for a single space like box or something to not have any chemicals or any elements in there? No.
Yes,
Yes.
it is possible in certain compounds, in certain elements.
No, but like just a box with no particles of anything.
And it still be an atom?
No, just in general, just like a box like this big, and just like nothing. In it.
No. I don't think so. I think that's a black hole level condition. Yeah. Or like a pure vacuum space,
Yeah.
which is, I don't even know if we might have created a pure vacuum. But usually we create a pure vacuum with the goal of something so it interacts with a specific particle, actually. We rarely just create a pure vacuum for the sake of creating a pure vacuum. But I honestly don't research that many projects because there's just endless, and half of them don't go anywhere. Half of them are corrected 5 years later. So I'm just kind of like waiting for the big ones. So what is each so if you have 7 suborbitals, each holds what? So what is our max amount of electrons? Carlos, what's our max amount of electrons? Yes. 14 electrons. You max out at 14. So now we get an actual model for the atom that 1 is now 3D, not 2D. 2 keeps the energy level part, but starts getting more specific in, well, where exactly do those electrons go? And then 3 adds another layer of, actually, there's subcategories of where they can go. There's zones, kind of like in an amphitheater. Have you guys ever been to the Granada? You're in like DD zone, HH zone, right? You got the orchestra, the pit, and then you have subzones within there. Then you have seat numbers, right? So we're getting more and more specific. So honors, by the way, your honors video is going to go into the next 2 levels. Okay, notice we've only hit up the 1st and 2nd level, but I said there were 4 for this model. Okay, the 3rd level, just for honors, you want to know this? The 3rd level is going to be a little bit what I kind of went into with the suborbitals, the shapes. So that's for honors. You're going to dig more into suborbital stuff. You're also going to dig into honors, the 4th level, which is spin. Are the electrons spinning up or down with the magnetic pulse in the universe? Okay, so this is all honors right here. This is an honors topic. And I'm going to highlight it differently so it becomes clear. This is honors. Okay, you're going to hit up levels 3 and 4. Okay, you could call the suborbitals, they could be like your street name, and the spin like your house number in terms of an address analogy. The suborbitals are like the street name, and the spin's like your house number for honors. Okay, so let's just do a quick summary, and then we're going to talk about electron configuration, how we write out the address, and then we'll be done. So Bohr model, I'm actually going to leave this as a warm-up. We're going to do this later. You're going to do this as a summary on your own. And let's talk about electron configuration. Okay, purpose. This is how we write up the address, okay, of an electron using quantum mechanical model, QMM. It's my shorthand for the quantum model. So the first thing that we need to know is, I've told you this already, but we always assume electrons will fill an atom's level starting from the lowest to the highest energy level, right? That's what we've assumed. We've already been doing that, but that's actually called a name. It's called the Aufbau principle. It's German. It's German for build from the ground up. That's I don't know like if that's the word for word translation, but that's the idea of the translation. I am not German, clearly. Okay. And I definitely did not take German. I took Spanish and I still suck at it. Okay. 5 years of Spanish got me nowhere, folks. Nowhere. Okay. You just have to move there. So let's look at an example. So let's say I want to know the exact address of every electron for the most part. Honors, you're going to get even more detailed, but I want to know the exact relative address of every single electron in the sulfur atom. Well, here's the thing. I know sulfur is going to have, neutral sulfur is going to have 16 electrons. So I need to figure out where all 16 of those electrons go according to energy level and orbital. Okay, so where do they go according to energy level or principal quantum number, if you want to get really specific, and orbital? Okay, that's what I'm trying to figure out. According to energy level and orbital, where do all 16 of those electrons go? So when you go to your periodic table, what you see is, this is the D block. You see, to get to sulfur, I have to fill up the amphitheater all the way all of these seats have to be filled to get to sulfur's place, right? Because again, we fill from the bottom up, and on the periodic table, bottom means lower energy level. Lower energy level is row 1. Second highest energy level, row 2. Don't translate lower as position on the periodic table. Think of it as actual what it means, okay? So I know that each of those boxes represents a place where one of my 16 electrons can go. And where that box is located tells me what energy level it's in and what zone it's in. So something to note, H and HE together make up the S, even though they're placed in weird places. They are the VIPs. There's only an S orbital in row 1, energy level 1. There's one zone. It's the most important zone. It's the limited zone. It's a VIP zone. There's no other zones because why? You ain't special enough to be there. They keep it small, right? So H and HE, hydrogen and helium, make up row 1, zone S. And we say how many are in there? 2. So what would we start to get to sulfur? We have to start by filling up. Okay, sulfur starts by filling up 1s2. That's how we write it. That 2 right there tells me the number of electrons. Okay, 1s2. Okay, so that's 2 out of my 16 of my sulfur accounted for. Let's move on. Okay, 1s2. Jeez. Okay, next stage. Yes. It is. It's in a position where it's in column 1, column 2, column. Because remember, I said the helium is special because it is part of the S. So now we look at, okay, if column 1 and column 2 are the S orbital, there's S zones. Okay, now we look at, okay, to get to sulfur, I now have to fill up this region next. Okay, I had to fill up 2S, what? 2S, 2S2, 2S2, 2 electrons in energy level 2, orbital zone S. Those 2 seats are filled because S orbital can only hold 2. Then I move on and I say, sticking to the same color palette, purple, I keep on going though because I'm not at sulfur yet. I fill up row 2, orbital, what? P, how many electrons? 6. 6. 1, 2, 3, 4, 5, 6. So going back, I say, where do the rest of my electrons go? 2s2, 2p6. 2 electrons are in the row 2 zone S. 6 more electrons are in row 2 zone P. I have a total of 10 electrons accounted for, but I need to count for where the other 6 go. So I keep going. And I say, okay, to get to sulfur, I'm going to go green now. I need to now bump up into row 3. 3s2. Am I at S yet? No. So I'm going to stay in the same color palette, green. 3p what? 4. 3p4. 1, 2, 3, 4. So my electron, what we call configuration, my address based on the quantum mechanical model becomes 3s2, 3p4. Notice my address builds just like how I fill my electrons. I start low and I fill up. And notice 2 plus 2 plus 6 plus 2 plus 4 is equal to 16 electrons. Yes,
So is the first number?
energy level.
That's, okay, the energy level, like the row.
Mm-hmm.
And then the second number is how many electrons?
Yep.
In that little section?
Yep. So I think that's enough mind blowing today. Let's stop there today. And we're going to have you guys work on your preparation for the test. So to transition, let me give you a summary of what the test is about. Okay. So I know we're learning new stuff as we review old stuff. Okay. So we're going to stop here for today. So here we're just going to stop today happens to be Valentine's Day in the year 2023. Okay. So stop here and we'll deal with the other stuff later. For your test tomorrow, this is what you need to know. You need to understand, okay, periodic table trends and Coulombic attraction. You need to understand that the more Coulombic attraction you have, the more likely you're able to interact with another atom, right? More Coulombic attraction, more likely that you can steal another atom's electrons. More Coulombic attraction, more likely you can, once in a bond, covet, greed, pull over more electrons. More Coulombic attraction, smaller the radius, right? More Coulombic attraction, more reactive overall. Because notice, all those things with Coulombic attraction make you better able to create an interaction with another, an electron exchange with another atom. So that's one thing that you're going to want to really understand is that Coulombic attraction naturally makes you more reactive. It makes you more likely to engage and interact with another atom. So in case you don't think you're going to remember that, I would write that down. Maybe just kind of a big thing to remember is big idea. More Coulombic attraction, more likely to react / get into a bond. Make some electron exchange with another atom, right? Make some electron exchange with another. That has been implicitly said, just not explicitly. And I think before the test, it might help you just to have that heard exactly said. More Coulombic attraction means smaller radius, okay? More electronegativity, more ionization energy, more likely to even just get interaction with another atom, which is always the start of a bond, of some type of engagement, okay? Then the other thing that you're going to be tested on for this test tomorrow is your Bohr model, okay? Your Bohr model. So using the periodic table, the basic model, general just energy levels, where do the electrons go? And of course, what are the most important electrons? The what electrons that help with bonding? Valence electrons, exactly. So excellent. That's tomorrow's test, is a combo of understanding how Coulombic attraction predicts trends, and therefore those trends are actually revealing reactivity, the ability to actually engage in a exchange of some sort with another atom. You're also going to want to know a little bit about your general metals and halogens, their general reactivity. We know there are special columns, right? And then the Bohr model. That is tomorrow's test. Okay. Honors, you have a video on quantum mechanical model and orbital diagramming. I would honestly just watch at most tonight the quantum mechanical model video. Pause the video once you hit orbital diagramming because it'll make more sense when I go over further electron configuration for the quiz on Thursday. So honors, I would splice your video just to focus on, if you even do it tonight, just the quantum mechanical model, not the orbital diagramming. It's just gonna be too much. But that's all I have for you today. And good luck.